Well, thank you, Kevin. And it's very exciting for me to be here because the only other two times really I've been here, one time I got lost and I ended up here by accident. The other time I was in an auto accident. So I hope this goes a little better, although you can tell me if we achieve either of those things in the course of the talk. So I want to tell you a little bit today about very recent work that we've done at Amherst and concluded on knot solitons in a quantum fluid, specifically in a Bose-Einstein condensate, a very, very cold sample of gas. This is work that I've done in collaboration with a Finnish group, a Finnish theory group led by Mikko Matonen at Aalto University, and then the other two people at Amherst, my thesis student Andre Horia-Gheorghe, and my postdoc who has gone off to better things, Mike Ray. And we're funded by the National Science Foundation. So I want to talk about knots, and I want to start out with knots as sort of something that in technology has been very important for millennia, really. And so this is an example that's sort of sailor's knots. It might be the first thing you think of right after you think of your shoelaces. It's like, what's a technology using nets, right? Tie rigging, things of that sort. And so this has been going on for, I don't know, as long as people have been around pretty much. It also is a theme that appears in art. And so here's some Celtic art. This is the Book of Kells, which is a manuscript from about 800. You can see the beautiful patterns. And you can probably see them without my illustrating where they are, but okay, these beautiful knotted patterns. And if you see images of Christ in these, in the Book of Kells, his beard is all knotted up in these beautiful ways. And so this is really extraordinary examples of art. You can go from there. Celtic knots take a turn for the Tattoo Me Now. So you can get these Celtic things put anywhere on your body, too. So I'm not sure anyone's tried to put the Book of Kells on his or her body, but it's an ambition that somebody could pursue in the future. They've appeared sort of all over the world. The Quipu knots from the Inca civilization were used, I guess, as, or as people understand, were used as mnemonic devices to help carry stories from generation to generation, or possibly as a kind of counting system. There's no Rosetta knot, so unfortunately this is not fully understood. These are all examples of knots, and if you look carefully, these knots, they aren't what we would think of as mathematical knots. A mathematical knot is something where you have a closed loop. So being an experimenter, I have a closed loop here, which is a BNC cable with a barrel connector. And so if I want to make a knot out of this, I can just connect my cable like so, and now I have a knot. Now this is a very boring knot. It's called the unknot, not to be confused with not a knot, because it actually is a knot, but it's an unknot, okay? And the difference between an unknot knot and a slightly more complicated knot is that I can introduce some other kind of knotty type thing going on here. Actually, it's hard to do with a BNC cable, as it turns out. I haven't tried that in advance. But now I've got a new kind of knotted structure, and it corresponds probably to one of the, I don't know, it's probably one of the 4 or 5s up there, right? So now it's a knotted thing. But it's distinct from the unknot because there's no way I can kind of go and twist it and turn it, and even though it is a BNC cable, I can't twist it and turn it. It's frustrating. Oh, well, I'm going to be frustrated because there's no way I can take this and turn it into the unknot. So this is the distinction between a sort of simpler topology, which is this one where I unwind it all. Notice what I had to do it. Disconnect it. And then when I reconnect it back, now I've got the unknot again. But there's no way to go between those configurations without taking advantage of the barrel. Now why did this, there's lots of ways you can get knotted. So why did this really arise? Well, the study of knots partially was initiated with the observation that there were lots of kinds of persistent flow that seemed to have kind of a knotty behavior. So what I'm going to do here, does anybody have asthma? Nobody will cop to that. Okay, well, good. So what I'm doing is I'm filling a box with smoke. And so this is an example of, sorry, if I hit you, I'm sorry. Actually, I might not be sorry. It might be part of the effect. I was telling Kevin just a moment ago, I did this to the dean without really warning her much. And I don't see how that goes with, oh my goodness. Okay, well, I think we might want to stop there. But this I get carried away. But this persistent phenomenon, of the smoke ring traveling through space. Okay, so that's actually kind of wild, right? Because if I were trying to blow smoke up to the projector up there where I see it's all gone, if I were trying to do that, I would have a difficult time just with my lungs, right? I could blow all I wanted, and I'm not likely to disturb the air up there. But by creating this kind of persistent unknot structure where there's a vortex of air, containing the smoke in this case, where there's a vortex of air which propagates along without changing very much, where the vortex is along the knot, the line of the knot. That's a remarkable thing, right? I could blow a styrofoam cup off someone's head. That's what I tried to do with the dean in sort of a William Tell moment. Just really didn't go well. So that was sort of the motivation behind some of this. And it turns out nature's been doing this for a long time. This is one I just found very recently. This is Mount Etna, which was blowing steam rings. They're about 10 meters across, and they'd persist for about 10 minutes. Okay, so it just sort of naturally these things come off. And there's an island that was being formed off the coast of Japan. You can also find this online. An island off the coast of Japan that was blowing out these steam rings. And they're remarkable things, persistent structures that travel for a very long time. And this got Lord Kelvin, William Thomson at the time, Lord Kelvin very interested. He thought, well, gosh, if we have these persistent structures that sort of propagate through the universe, maybe actually there's something to this. Maybe if we could have different knotted forms that would propagate along in the ether. And then each of those things would be an elementary atom. And different atoms or compounds of atoms would be where the knots came together and made new knots. And this was sort of the vortex atom approach. Of course, it's a total bust as a theory because there's no ether. And atoms aren't vortices as far as we know. But it is a kind of string theory if you think about it. So it's kind of interesting. Actually, the knot table I showed you earlier really is due to Peter Tate, who, following Kelvin's work, was very, very interested in sort of, let's outline what all the knot possibilities are. And you see these are all counted. The number, I guess, is the number of crossings. This is the famous trefoil knot. They're cloverleaf knots. All the times that one part of the curve crosses another gives you the first number, and then there's the A form and the B form. You go on and on and on. There's all kinds of knots. Just very recently, people have started to actually realize some of these more complicated knots. So up here, this you recognize as the unknot. This is that trefoil knot I showed just a moment ago, and you can actually get it where it's a persistent propagating structure through water with all these little bubbles outlining where it is. This is very new, as you can see. Just a couple of years ago, people are starting to do this in water, just in water. This is my favorite example. You don't often probably think of plants as generating vortex rings, but here's a plant, a little moss, that has to launch its little spore high in the air. And how's it going to do that? Well, why does it want to do that? First of all, because spores, when they get high enough, there are prevailing currents that will take the spore somewhere else. If you don't get it high enough, it comes right back down, lands on you, and competes with you. So this little plant generates a little vortex ring, seats its little spore on top of it, and off it goes. And then that spore goes way up in the air. Precisely is how I could send my smoke up to interfere with the broadcast of this thing. Dwight Whitaker, who did some of this work, is an old atom trapper BEC person who was at Williams when he did this work. So just this, we're sort of a eclectic crowd of scientists, I guess. There are also knots now in optics. You can create knotted structures where, again, it's kind of like a vortex. It's actually a thread of darkness. It's sometimes called the vortex of darkness or something, where you have this light and then the phase of the field wraps around the line which defines the knot. So it's a bit like the vortex in water or the vortex in air, or the vortex in ether for that matter. So this is a trefoil knot that's been realized, and this is a computer reconstruction of their data. So I guess I would call that data. And people have been knotting things like DNA. So again, you have a line, you follow it around with your DNA strand, and so these are things that people have been doing for some time. So we've now seen two examples of knots, two types of knots. There's sort of the sailor's knot, the shoelace knot, and then there's this sort of mathematical knot. And what I want to talk about now is sort of shift slightly into the knot soliton. And the knot soliton is, the ON in soliton suggests something about particle-like kind of thing. And the knot soliton is a collection of knots that are all linked with each other. And in this particular case, this is an electromagnetic knot. Each of these each of the links of this knot, each one is an unknot. Okay, so this is a whole bunch of linked unknots, really. But that structure is called a soliton, knot soliton. Each of these links is a magnetic field line. So that would be a very simple example of a knotted electromagnetic kind of scenario. And this guy, Ranyada, worked out that there are solutions to Maxwell's equations that look like this, where there's a whole bunch of field lines that are all linked together exactly once. Each one is an unknot in this case. And one of the more interesting things, I guess, is this idea that you could actually explain ball lightning with it. He's actually gone through several iterations of a model in which ball lightning is a plasma constrained by this magnetic soliton, knot soliton. It's kind of a remarkable idea. So yeah, well, we'll see if that actually pans out. This is a hard experiment to do. They only just now are finding ways of analyzing ball lightning because it's hard to generate in the lab. But one question might be, could you actually generate some kind of knotted structure like this and do that study? By the way, this also suggests the persistence, because your magnetic field line has to point in a particular direction. And so if this thing is kind of stuck together topologically because the links can't actually pass through each other without the field going to zero somewhere. So this is actually part of this persistent kind of feature, the knot soliton. And knot solitons have appeared in classical field theories for a very long time also, much longer than this, but this is 1997 is where people began to realize, oh, hey, you can actually find these solutions. And so here are some solutions with knot solitons. These are the cores of the knot soliton. This is the shape of the core, so kind of an unknotted thing here. And then all the other links in the knot soliton would be linked with it once. And then as you move down, here is another one that looks like an unknot. But in fact, when you make a knot soliton, each of those is linked twice with all of the other links. And you can work your way down. Here's kind of a figure 8 kind of core. And then everything else is a figure 8, all linked with that figure 8 and all of the other figure 8s 3 times. And you can kind of work your way down. So this is a bit like Peter Tate's knot tables, only this is how it goes in the classical field theory. This is the kind of knot soliton that I want to tell you about today. We are not going to go any lower than 1, okay, because that's hard enough. But if you're interested, you can find your way to 8 or even higher. So to give you a little bit of an understanding of this, I want to work in 1 dimension. I'm not going to be able to talk about things in 3 dimensions without getting this. 1 dimension is going to be a good starting point. And in my field theory, I'm going to imagine along this 1-dimensional line that I have some background field, and the field always points in 1 direction. That's the absence of everything. The absence of everything actually involves a vector field with a definite direction. And this is kind of a funny vector field because these arrows, I'm going to allow them to rotate about this axis, and I'm going to represent where they are by a point on this circle. Okay, so if they're all pointing up, they're all sort of pointing up to the top of the circle. And then I can rotate them and do different things just to show you this feature, the soliton feature. So I can flip one of them around, and then I have some kind of discontinuity. And this is what I would call the core of the knot. This is not a knot yet, okay, so we're getting there. But the core is where you take the field direction and invert it. So it points the other direction. That's what you call the core. Now, all around that will be these other things going on. It'll take a while to get there, so hang with me. There's the core. That particular structure was very discontinuous. And I'd like to imagine, as is the case with a knot, that we have a continuous kind of so-called texture where this background rotates in a continuous way into the core and then rotates back out in a continuous way out of the core. Okay, so you can see this thing, this particular structure, it goes, all these shapes are over here, all the arrows point on this side of the circle. So this would be an example of some kind of spin texture. Now this actually is not topologically, if you like, distinct from the case that we just looked at originally with all the arrows pointing straight up, because I can unwind it by just rotating my arrows back. And so there I can wind it in if I like. Okay, that's a continuous operation. I didn't have to break it in two pieces and do something funny and then plug it back together. I'm just sort of just switching it, just doing that little rotation. Are you with me so far? Okay. Gets a little harder. So what does a knot look like then, or a soliton look like in this case? It involves a rotation that goes all the way around the circle, if you like. And so you can see it rotates to the left. Now here's the core, and then it kind of keeps rotating and rejoins the background. So you would call the location of this soliton here, and then it's got these arrows that sort of link it into the background in this continuous way. Okay, that's what we want to do in 3 dimensions. Okay, so if we get this idea, then it will help. In 2 dimensions, this is known as a skyrmion. This is a 2D skyrmion, actually. And you can see, again, there's sort of a core. The color scheme is different, but the core is an arrow pointing downwards. And then the background is this set of red arrows which point upwards. And then you go continuously with your texture, with your arrows, and between down, the core, and up, which is the background. Okay? And in fact, what you see is our soliton. If you took any line through this structure, you would see exactly the 1D soliton that I showed you a moment ago with that rotation. And this has been done for some time in the condensed matter community, skyrmion crystals even, all kinds of fun things. So I want to do this in 3 dimensions. So what does that look like? Well, first of all, we have to imagine, oh, sorry, there's a question, please. This one? Great question. No, there's another way it could go, which is more fountain-like. So it actually comes in, isn't it? Yeah, just radial. So in this particular case, this is a kind of way of representing. But you're absolutely right. That's another texture that meets our criteria of continuous and flipping around in the middle. Okay, so thank you for the question, by the way. That's perfect.
Sorry, one more quick question. You mentioned that the other one was not a soliton because it couldn't be unwound.
This guy.
Right. So this one, if you did try to just do a continuous rotation of all this, it would not be possible to unwind it?
Oh, the 2D soliton.
Yeah.
That's correct. There's no continuous way of unwinding that without going and making it 3-dimensional and doing something different.
I'm having a hard time visualizing that, but I don't know.
Okay, well, the 3D part's going to be harder. So you can. No, you can. If you need a seatbelt, you can just tie you to your chair. Okay, so, oh yes.
So it looks like in the unwound case you're rotating clockwise and then counterclockwise.
That's.
And in the other case you keep going in the same direction. So does that generalize?
Let's see.
Or is that
I think well, the way I mean, it still looks to me. Oh, not in this case.
The 1D example.
Oh, the 1D example here.
Right. So you sort of start going one way, then you sort of reverse.
It's the same kind of thing where I imagine it's just you go around once. So it's like a helix.
One behind this. Previous
Oh, the previous example. Yeah, I just go down and then I
here
come
you
back.
just kind of go down and back.
Yeah, right.
So is that generalized to all dimensions? Meaning basically if you go
Oh.
all the way around it's knotted, and if you go around and then you go back it's not.
Yeah, it is related. There's a charge associated with this in more dimensions. So we have to find a particular configuration. One doesn't spring to mind immediately, but one could imagine locally distorting the direction of the spin in a continuous way and having that be topologically equivalent to all the vectors pointing in the same direction. So I don't have an immediate plan for that. Thank you. Okay, so here we go. Here we're back at 2D. Okay, so 3D. So the first thing we have to imagine, even before this, is a slide I forgot, which is just all the arrows pointing upward, which is space before you've introduced anything. Now, I want to have a soliton in it, and I want it to be of the character of an unknot. So I'm going to create a core that looks like an unknot, and that's represented by this white ring, and all the arrows on my white ring point downward, because that's what the core is. It's the opposite of the background. I'm going to represent my arrows now also on this little sphere here. This is just the unit sphere, and each of my little vectors will be unit length. So if I want to look at this core, it's going to correspond to the south pole of this unit sphere, because that's where, if you go from the center, your arrow goes down and touches the south pole. Okay, so this is the core. Now, this unit sphere is actually kind of useful in another respect, because I can pick another direction on the unit sphere with a little unit vector and have it point that direction, and there will be another ring in space up here that corresponds to that particular choice of arrow. So what might that look like? So here's one that's sort of, I don't know, you could call it the x-axis. It's a green arrow, though. And if you looked at all the points in space, in this way of breaking down the problem, if you looked at all the points in space that have an arrow pointing that way, it's another ring. It's another unknot. Okay? And that all of the arrows for that ring point that way. So in some sense, this is kind of a funny mapping. I'm mapping arrow in a particular direction into this funny space here, which is just a unit vector pointing in some direction on the unit sphere. So let's pick another direction. That's another ring with another arrow direction, another point on my sphere. And I can start to kind of put these together now. And you can see that this ring, the core here, is linked with this green ring in this way, one link. And then so then we can fill in some points on the equator. I'm going to remove the arrows because it gets confusing rather rapidly. But there's the blue ring, and it's linked with the other two rings, each one individually once. At that point, you can actually go to Crate and Barrel and buy a napkin ring, which is actually exactly this. It's not a Borromean ring, right? Because if I break one ring, the other two are still linked together, right? A Borromean ring is different. But this is an example of one of these structures. It's 3 rings. But of course, my sphere has much more room than 3 rings worth. It has 4 rings worth. Well, actually, it has 5 rings worth, each one linked with all the others. And of course, I'm kidding you, right? Because there are lots of rings you could add. In fact, there's sort of infinity of rings that you could add. Here's some rings along the equator, just so that we could see the core. In fact, the thing closes in on itself like a donut. It's a hollow donut, not a very tasty donut. Maybe the core is tasty, I don't know. Okay, so we have the south pole. Here's a lot of the equator. Okay, and then we can also, I can't really depict the entire background because, of course, the entire background would include the knot itself. So I've just drawn some. This is near the North Pole on my sphere. Okay, so the North Pole would represent all the arrows pointing straight up. That's the background. The knot soliton is this localized structure which consists of a core and an infinite number of rings around it, including the rings that go continuously into the background. I probably should have pointed that out. Well, actually, this is probably as good a place as any. Here, that really you do go continuously from the upward pointing thing to the core along any path that you take. This is kind of a remarkable fact about this thing. Even though I don't think I can prove that to you here, right? Because you'd actually have to take paths. But one thing that you can sort of tell, the color here, let's go back one. The color here on the equator, these are all the arrows that point horizontally. And you'll notice the color goes all around. If you go around this toroid toroidally, you go through all the colors exactly once, which means you've gone through all the directions this way exactly once as you go around the outside of the torus, or on the inside of the torus. But not only that, all those arrows go around once if you go poloidally, here's where the board is, poloidally, right, which is towards and away from the pole. So you see you go through all those colors. You go through yellow, red, blue, green, and then you come back to yellow if you go poloidally, and you go toroidally as well. So it's a remarkable structure, this thing where these vectors are going around in this continuous way. Yes?
So what's the reason for going from a 1D core to 1D core to jumping up to a ring? Like, would it be possible to start with a point like core?
That's just pointing down and then try to work your way out from that? You can't do it continuously. I think there's just the symmetry of the problem. This might be an instance, does anybody know the Harry-Ball theorem or something? You can't actually do what you want to do with something that just starts down. But if you have a core, you can continuously wind into it. Because you imagine, come from a point. Now, how do you continuously turn it up without breaking your symmetry in some way? Maybe there's a way to do it, but no, there isn't a way to do it. I can tell you that. But it's a great question. It's a great question. Yeah. And I haven't proven anything here. I've just shown you the structure. I've just shown you this structure. Yes?
Because B and A are related to the curl, I'm wondering if there's a dual A knot that goes with the B knot. This is actually similar.
Dual A knot that goes with a B knot. I do not know. That is it's a very interesting question. A dual knot. I don't know. I've never run across such a thing. But for those of you, though, who recognize topology in its many forms, this is an instance of the Hopf fibration, which is a way of taking space and dividing it up into donuts. Each donut is made up of all these rings. Each ring is linked with every other ring exactly once. I've just shown a few here using my funny little sphere. Okay, it's a mapping from real space, in this case, onto the surface of this unit sphere. It's a very beautiful structure. It's sort of a foundational piece of topology, and it's due to Heinz Hopf. And it's really, strictly, it's a mapping between the surface of a three-dimensional sphere in 4 dimensions to the surface of a two-dimensional sphere in 3 dimensions. And if you enjoy thinking about that, then power to you. But actually, we kind of cheat a little bit, because in fact, S3, this surface of a three-dimensional sphere in 4 dimensions, can actually be projected into real space. Okay, so real space and S3 we don't want to draw too sharp a distinction for our purposes. Otherwise, I would have to tell you a different talk about how we did something cool in S3. Remarkably, this Hopf fibration appears all over the place in physics, as you might imagine. For those of you who know the Bloch sphere, we are playing around with the surface of a Bloch sphere and looking at vectors, so maybe that's not too surprising. I had a marvelous moment when I realized that, in fact, it's central to sort of the theory of Dirac monopoles, which suddenly my research program, which had never had coherence before, suddenly was granted this coherence, and that was just a marvelous moment. So this appears all over the place in physics. So that's knots and not solitons. I want to just very briefly tell you a little bit about spinor Bose-Einstein condensates. And first, just Bose-Einstein condensates as a starting point. They're superfluid droplets. They're cold, billionths of a degree above 0. They're in a very controllable and pristine environment. That's sort of one of the central interesting pieces. They're coherent. If anyone has not seen this matter wave interference experiment that was done at MIT in 1997, you should go immediately run, don't walk, and find this paper, because it's a remarkable demonstration of matter wave interference using 2 of these coherent sources. And it's superfluid, which means we get emergent collective behavior. And so this is not my idea. This actually belongs to Grisha Volovic, but if you think about the Bose-Einstein condensate, it's made up of a whole bunch of atoms. But this isn't how I want to think of the thing. Because of this emergent collective behavior, I want to think of it as the background in which a lot of things can swim around and move and exist. Okay? So the idea here is I'm interested in topological excitations primarily. And so things like vortices that could be running around inside a Bose-Einstein condensate, Dirac monopole, possibly an isolated monopole, and the subject of this talk, which is really the knot soliton. We're going to create it. It's a quasi-particle-like thing that goes inside this background where it's the universe. Okay, so that's how I like to think of this particular problem. We make these things in an atomic physics tabletop kind of apparatus, which doesn't look half as cool as Kevin's awesome tabletop thing that I'd like to steal and take with me to Amherst, but I only have a small car. So, well, anyway, it does just fine for us. It's small, it's a little old now, but it's still my favorite. Optimistically, I call it BEC1, but I'm not sure there will be a BEC2. And it has lots of lasers and a vacuum system and currents and coils and all this stuff. And this is what it actually looks like from the top. So it looks like an atomic physics experiment. Just to give you a little theory on the Bose-Einstein condensate, we can talk about a scalar condensate, and we can just write an order parameter for it. And this is like a wave function, a macroscopic wave function, and it's got some normalization, normalized to the density, and it's got some phase. So that sounds good. And it obeys some kind of Schrodinger-like equation, a nonlinear Schrodinger equation in this case. But it's basically it's quantum mechanics. It's sort of straight up quantum mechanics. The additional part that we add to this is the fact that the atoms have an internal spin structure, and we're going to work with a very simple spin system, F equals 1, and so that's the total angular momentum, F. And so we'll just include a spinner to represent the spin components of our condensate. And so here are the 3 levels, and this is the spinner we'll use. So it's really just a multiplicative thing. The only thing that's about this that's probably a little tricky, we're used to thinking of spin, and you think of the orientation of the angular momentum in space, okay, right? And that's sort of like this picture here, even though this is a little funny, that's sort of one of your spherical harmonics here. Really, you're looking at the phase. Red going to blue is really the phase of this thing, and that's sort of like what the Y11 looks like. And that's sort of the ferromagnetic phase of a spin 1 kind of object. And so it's all the rotations of this 100 spinner. That's sort of the spin-like thing. But there's also another thing that's sort of very similar to it, but it's where you start with 0, 1, 0, where everything's in the m equals 0 component when you start out. And then that's what's called polar. And it still has a direction associated with it, as I've sort of depicted this Y10 in this kind of screwball way. But there's still a direction associated with it. It's not a spin, okay, but there's still a direction. Okay, so I just want to highlight that because that's the vector field, if you like, that we're going to be using. Okay, it's a little more abstract than actually having a spin pointing in some direction. It's really, it really has to do with the direction of this thing. How does that work? Well, imagine I've got my spinner here, which is 0, 1, 0, and I apply some spin transformation to point it in a different direction. Okay, so there, it points in a different direction, surprise. Okay, so that's a spin transformation that would correspond to a rotation in real space. Now, if I attach a vector to this, it's a unit vector. Okay, so let's say it points from the blue side to the red side. Okay, this spinner transformation just corresponds to a vector rotation in real space. Very much like if you had a spin, and there's sort of a vector associated with that, and you rotated your spin, then you have a vector that comes along with the spin for the ride. Okay, but this is not spin. This is a director. Those of you who know of pneumatic directors, where you have a rod-shaped something or other, and it rotates like a liquid crystal kind of thing, this is the same kind of thing. In the liquid crystal, it's the axis of this funny liquid of the crystal. So here it's just some rotation of this 0, 1, 0 state. It's okay if you think of it as spins. That's all right. Just between us. I won't tell anyone. Okay, but I just, to be honest, it's not a spin. But there is this one-to-one correspondence. And if you're curious, this is the relationship between those spin components and the components of the vector. Importantly, even though this is not a spin, it does precess around magnetic fields just like a spin does at the Larmor frequency. So now you're saying, well, what's the difference between it and a spin? They're different. So I can write my order parameter instead of using a spinner. As long as I stay in this polar phase, I can actually turn it into kind of this a scalar part times this sort of unit vector. And if you think about it, this thing here, what is d? That points somewhere on the unit sphere. And r, that's some point in space. So all we really need to do is come up with a clever way of steering our d so that we can realize this mapping of these unknot loops, these rings that are all linked with each other, into S2, which is the surface of the sphere. So I'm going to cleverly pick D. Well, actually, I've already picked D. I've told you it's the Hopf map. OK, I'm cleverly going to experiment to find the right D. So that's really what the remainder of this talk is. There was some really great theoretical work I just want to highlight. The Kawaguchi, Nitta, and Ueda paper where they titled Knots in a Spinor Bose-Einstein Condensate. That was on the phone. It was like somebody called me up. OK, let's do that experiment. And there's also been some really great inspirational experimental work, and I want to highlight one of the faculty here for having contributed to that. In fact, I stole your figure. OK, so how are we going to do this thing? So let's imagine the green thing, that's our Bose-Einstein condensate, and the blue arrows are the background magnetic field, because we're going to use magnetic fields. And I've just thrown in a few directors into this thing. Now, actually, this thing is chock full of directors, and when we start, it's the background. There's no soliton, there's no knot, there's no nothing. It's just a whole bunch of arrows all pointing up. But I didn't want to show all those arrows, so I've just picked a few key arrows to show the general idea. Everything's initialized. We got this nice field. Now we're going to change the field very suddenly. And we're going to make it into this sort of magnetic quadrupole character. Now, this is really easy for BEC people to do. It's like any time you put current through two coils in opposite directions, you get this kind of thing, which has a 0 of the field here and then this sort of quadrupole character outside. Okay, we have to have the divergence of B remaining 0 because this is not a monopole experiment. But the way you do that is you have field lines in this way. We do this very suddenly. So all these directors are pointing in the same direction as when you started. But now they precess in this magnetic field just like spins do. And so they will undergo this kind of rotation, which I've kind of represented by this sort of orange triangle things. Okay, so this guy's rotating around. The tip of the vector is rotating around. This guy, the tip is rotating around, all perpendicular to the field lines in their way. And of course, as you go further away from the 0 of the field, the Larmor frequency gets bigger. So those sort of further out in the condensate are rotating much more quickly. Those closer in fact, this guy in the middle, I didn't even bother putting an orange arrow on him because he doesn't rotate at all. It's right at the middle where the field vanishes. Okay, so this actually, surprisingly, is what winds a knot into the condensate. This is as simple as the experiment is. We're an undergraduate institution. This is it. I mean, we could do much more complicated things. But this actually turns out to be a really easy thing. And it gives you something new. Bear with me for just a second. This is the 2D soliton shape. This is looking down at the state of these directors after we've done some rotation for a little while. Bear with me. It's a little tricky. This is the 2D soliton, except it's a little different. I have a core now. Those X's represent arrows pointing into the plane of the board. This is the core. The background is out here. These are arrows pointing out of the board. And there's also background at the very center. How did I get this? I started with my spins rotating. The Larmor frequency is largest the furthest you go from the center. Okay, so first of all, the Larmor frequency is 0 in the center. So my upward directed director there doesn't go anywhere in time. It just stays put. As these directors start rotating around the field line, here's the field lines, these blue lines going out. So each director is going to rotate around its field line at the Larmor frequency, which means the further out you go, the more rapidly it's rotating. In fact, we can just freeze the picture after the guys on the outside have done one 2π rotation. And that's a continuous rotation, which means halfway to that point, it will have only rotated halfway. And that's the core. It's cylindrically symmetric here. Okay, we're just looking at one slice. So on the outside, it's gone around once. In the middle, in the core, it's gone around halfway, pi rotation. And in between, it's rotated here 3π/2, here just π/2 in this nice continuous way. And you see we've sort of recaptured the 2D soliton shape, except now we have a circular core rather than a single point, which is rotated. Is that good? Okay, that only tells you about the plane. Then I have to throw something up which is sort of a little even weirder. And I might not try to go through this entirely, but you can get the idea. I'm sort of blowing up this little region here looking from the side. Somewhere out over here, the director has rotated by 2π. That would correspond to this point. These are all the directors. So they start with the black arrows. They all point up, black arrows. And then after the rotation, this guy is rotated by 3π/2. This arrow is pointing into the board here. That's this arrow. Okay. Right here, this guy is rotated by π. That's this arrow. Right here, this guy's rotated by π/2. That's this arrow. So that's that section looking through here. That's this. Along this dotted line, those are places where the arrow has rotated to point in the horizontal plane. This guy up here, has done a pi rotation about its own field line. This guy has done a pi rotation about its field line. And I couldn't do the same thing with all the others. But you can kind of get the sense of what's going on as you move yourself out of the plane. Notice you go all the way around the colors here as you go around this loop, yellow, orange, purple, and so forth. You go around once that way. And you go around once this way. And that's the toroidal and poloidal rotations as you go around each direction. I don't know if you remember that. Oh, we'll come back to it. Oh, we'll come back to it right now. Not as tide. You have to trust me on that, because otherwise it's really, you can go through the math, and in fact that's it. These are the horizontal directors. These are the places where there are horizontal directors. Here are the colors associated with them. This is the background again, and then there's the core in the middle. So just imagine taking sections like the ones I just did, and that's what you would find. Okay, good. I'm glad I thought you were going to tell me I was out of time.
Oh, no.
Okay.
I think I can see it from your drawing, but the symmetry of the quadrupole field, you're
Great.
depending on having the winding come to 180 degrees, 360 degrees at the edge of the cloud.
Mhm.
And so you're going to match the shape of the cloud profile to the magnetic
Yeah.
field. You actually had to adjust things so that how sensitive is if you're spinning the universe around
Yeah.
360 degrees, you've got to have the edge of your universe.
It's a lucky thing this fits. But in fact, all you have to do is make it small enough that it does fit, right? Because there's always a way to make it fit. But
I'll talk to you later about that.
yeah. So and there's another subtlety there which has to do with a factor of 2 to make the divergence of B 0 in the magnetic field coils. But that's just scales the vertical. Okay, so I'll let you puzzle over that. And don't ask questions about that yet. Okay. So now we got to detect this thing, and this is actually where it gets kind of cool. So to image our condensates, what we do, they're just too small. In the trap, they might be these little tiny things, much smaller than this, in fact, maybe only 7, 10 microns across or something. Very, very small. And so even though we've got some good optics in there, we really can't see anything like a knot. That's just not going to work. So what we do is we release these condensates from the trap. They fall, they expand, and then by the time they've expanded for quite a bit, we can actually look inside and see, well, what kind of structures have developed as a result of whatever we've done. And so these are sort of typical false color images where as you go up through the color spectrum from blue and purple up to white, that's more dense. The atoms are more dense as you move through those colors. So no atoms out here, more atoms in the middle. And again, these are, I didn't say this, but they're sort of, we're not taking three-dimensional pictures, right? These are projections. Column densities is what we can measure. The light passes through the atoms, it's absorbed. We sort of measure shadows. We don't know you can't always just look at that and say, oh, I know what's going on three-dimensionally in there, right? Because it's all sort of smushed into a plane. But what we can do is we can say some things about cylindrical symmetry and things like that. So that will be helpful in a moment. The other thing is, in detection, we need to be able to figure out how the spin components are populated, because that's going to tell us something about the orientation of our director. Okay, so a director pointing straight up is going to look different in terms of spin components than a director pointing sideways or a director pointing down. Yes, Jacob. Yeah. So that's a great question. And so what we're really doing is, what we don't have is true self-similar expansion. So whatever we have inside the trap does not expand and look exactly like what we had inside the trap. So what we do to back this up is we have simulation of what goes on inside the trap. We simulate the expansion, and then we look at what happened, look at the agreement after expansion. So what I'm going to show you is, I wouldn't call it a swindle at first. I would call it beautiful data. But in order to truly see what's going on, you have to rely on the simulation, because we can't access it. But when you see the comparison, I think all sins will be forgiven, I hope. So I just want to return for a moment then to this idea of the spinner. And remember, the spinner is this polar phase thing, and it's the 0, 1, 0 kind of thing. And that corresponds, if it's 0, 1, 0, that corresponds to director pointing up. And if it's 0, minus 1, 0, that's director pointing down. And the funny thing about this is that we actually can't distinguish the sign when we take the photograph. So we will end up finding all the points in space which correspond to vector pointing up and director pointing down. We get them all at once in one picture. So we get the North Pole and the South Pole by taking a picture and then looking at what appears in the central component, the m equals 0 component. North Pole and South Pole. Well, look, North Pole, that's this background. South Pole is the core. And here's our picture, experimental picture, showing the background. I mean, you can see it, right? You can see the background, which is the sort of mushroomy cap shape, and then the core goes around it. Okay, yes, it's flattened. It's because we have to, because there's no way to around it. However, we have done tomographic imaging where we look at slices of this thing, and you see it very clearly. I wasn't able to attach it in the talk. You see it very clearly, a thin central shaft with a ring around it, the core, and in fact, there are two rings because you can just barely make out the thing at the very edge, which is where that director is rotated through 2 pi. Okay, so when we take this picture, the other thing to note is that there's these black regions. And the black regions are where the director points in the horizontal plane because we don't detect that, right? We only detect the vertical parts of the north and the south pole. The equator is not accessible in this kind of photograph. So you can actually almost just sort of squint you don't even really have to squint your eyes that much. That's the torus. Core is inside the torus. Then there's the donut shell torus, and then there's the background outside. We just can't see the torus in this particular picture. Ah, yes, here. Yes. And we're focusing on this one.
So is that what happens, or is this the first step to make sure that you're all in that m equals 0 state, and then
Yes, so we start in that m equals 0 state. The things evolve, and then we look only at what's in the m equals 0 state at the end of the experiment, or at least for this experiment.
and so is that why you can't see
The torus? We can't see the torus because it appears in these two components. Yes, that's right.
So how does this work? Because if your directors are not actually a spin, then how is your magnetic field allowing you?
They're not a spin. Sorry to do this to you, but this is a PDF. Here it is. There's a one-to-one relationship between the components of the vectors and the components of the spinner. And you can see that right here. dz appears only in the 0 component, and x and y, which are the horizontal equatorial points, appear in the plus or minus 1 components with this funny phase. That's a great question. Thank you for asking.
Did you not take images of the other?
Oh, we did. I'll show you. All will be revealed. And sorry, avert your eyes for a second, because that's so annoying. I once made my mom throw up by doing that. Okay, so here's the torus. Okay, and inside's the core. So this torus, the equatorial points, here they don't appear in the 0 component, so you don't see them in the 0 component. So that's why there's that black gap. So it's just saying the same thing you asked about. Let me just show you. I want to show you how this winds in. Now, I've never actually tried to do this in a live presentation. Our experiment has progressed to the point where we can actually take photographs of these 3 spin components and just do one realization after another. Okay, so each picture, I have to destroy the condensate, or my student has to destroy the condensate to take the picture, right? So we start, we do all the experiment, we let it evolve, then we have to let go of it, take a picture, that was it. And so then in order to do it again, we have to repeat the whole process. If you want to do time evolution, you have to repeat this over and over and over. Our experiment has now progressed to the point where we can do that. And so what follows is a 500 microsecond evolution made up of 50 pictures that were taken sequentially, which I would not have believed was possible in the future, because actually a 1 milligauss shift in the field will take the 0 of this quadrupole field entirely outside the condensate. So you have to I mean, this is a remarkable thing, what I'm about to show you. I mean, if I say so myself. So what we'll do, so here it goes. I think somewhere there's a way to make this bigger, but, well, that's sort of pathetic. Ah, there it is. Let me back up. Let's try it again. So what we're looking at now, this is the 0 component in the middle, -1 component here, and +1 component here. So these are going to be the tori, I guess. And this is going to be that thing that we were just looking at from the side, which has that, oh, shoot. That's the problem. Haha, I'm showing you the wrong video. That looks strange. OK, we'll try this again. Here we go. The 0 component from the side, the -1 component and the +1 component from the side. This is the thing which will emerge and turn into that funny mushroom cat with the ring around it. Okay? This is a 500 microsecond film, which I will have expanded into 5 seconds or something. Okay? Now, as this winding goes on, so we're looking at a time progression, as the winding goes on, the location of the core moves inward from the outside, right? Because we start with all our vectors pointing straight up, and then at the boundary, at the outside, at infinity or something, the vectors start to go around, and they all kind of go around together. So eventually, the point at which the vectors are pointing down starts to enter into the condensate, okay? And then eventually, the vector where it's gone around 2 pi will start to enter into the condensate, if you want to think of it this way. The better way to think of it is just to say at the edge of the condensate, it goes around, and at some point, it goes through the core orientation, and eventually comes back to the other orientation. In fact, it would keep going if we kept going. So with that in mind, let's back it up. So when we start out, almost all the atoms, well, actually, when we start out, all the atoms are in this 0 component, which is everything spin up. And then as things go, you can watch this core come in right about here. It kind of bounces around a little bit. But you have to realize this is 50 sequential pictures. I threw none of them away. OK, which I thought was kind of cool. Now, you can look at that from the top as well, and that's what I did a moment ago. And that's also kind of cool, although slightly harder possibly to see. Again, this little button is hard to find. Let's go backwards here. Stop doing that. OK, there we go. So here's the evolution again. And you can kind of see the core come in there. It's a little bouncy, but you get the idea. OK. So that's what's going on. The directors are rotating. They rotate through this pi. Okay, and wherever the pi rotation is, where they're pointing down, that's the core. And then we can see that. Getting back to the question about the other spin components. This is the simulation here, and this is what we actually measure. You can even make out some of the finer details. Again, the simulation is looking at the column density also. We wouldn't try to compare a 3D thing to a 2D thing. But in fact, you can actually make out many of these same details in this kind of very remarkable way. So I would say we have very good agreement with that, and we expect this is the structure that we want to get. However, you could say, well, this doesn't much look like a torus. Right? That's that tube within which the core would exist. That does not much look like it, and that's this problem with self-similar expansion. It doesn't work. So then you look backwards at the simulation. And the simulation actually does show that. And so you can connect with the simulation this shape exactly directly into this one, this into that, and this into that, although I can't hope to tell you why it does that strange thing that it does.
Is actually the circulation around?
There's actually 0 circulation, so no. So I don't really understand why it does that. I mean, it has something to do with, OK, there are other things going on, right? We do this magnetic separation of the spin states. We're releasing them from the trap. They're no longer trapped. As they fight each other, as they expand, maybe they expand anisotropically. If you stand on your head, though, you do see that this is basically on your head of that. So there is something about that. It's kind of interesting. OK. just to finish this off, because I know I guess I really run out of time. We can pick a different quantization axis to choose as our quantization axis. Okay, we could pick the x-axis, which means looking at vectors that are either aligned with the x-axis or anti-aligned with the x-axis. Okay, so before we were looking at the spin component 0, and that corresponded to director up and director down. But I don't have to pick that as my basis. I could pick director right, director left. Okay, and then what appears in the in the spinner 0 component is the points in space which correspond to director left and director right. And if we take that, here's what we expect. We expect to see the 2 rings, just those 2 rings now, not the core, not the background, but just the 2 rings, and they make this kind of X shape because you're looking kind of at them from the side. I mean, it's remarkable. Those are actually, in some sense, the rings of the Hopf vibration. They're equatorial points, opposite equatorial points, appearing in the m equals 0 component. Or we could go, instead of right and left, towards you and away from you. And here you can actually see the rings. Those are 2 linked rings. Now, okay, yeah, they could be linked, they could not be linked in terms of the picture, right? We've smushed it into a plane, but given everything else that we have, I think it's plausible to believe that those are actually the rings. We're imaging the Hopf vibration ring by ring, or 2 rings at a time, 2 linked rings. And so this is the full picture of that. You can take pictures along 2 directions and look at those rings. This is what we're expecting. This column is what's in the trap, and of course, sometimes the expansion is a little weird and gives you strange shapes, but in all cases, our shapes are agreeing with the simulation after the expansion. So I think it's pretty compelling. And so this really is the end. This is the first knot soliton that's ever been tied in a quantum fluid, and it's going to appear in May, I guess. It went online. You know, they do this advanced online publication, and then, like, I don't know, 20 months later, they put it in the print, so I don't know about that. But it's apparently going to appear in May, so looking forward to that. Knots, one of the big questions about knots is, are they stable? Mostly field theory say, no, they're not stable. So we don't expect this to be stable. In fact, we're winding it all the time. We have to figure out how to stop winding it and then sort of look at it. So that's coming up. Could we make knots with higher charges? Different, if we went back to that thing where the core is linked with all the other rings twice, say, or it's a figure 8 linked 3 times with all the other rings. Not with magnetic fields, probably, unless we do something very different in another universe. But there are possibilities that we could do that in using some kind of optical plus magnetic technique or something like that. That would be fun. One of the stranger things that turns up from time to time is where you mix topological excitations together by accident. Here's a knot with a vortex line going right through the middle of it. So here we're kind of coming up with new and different structures where, what the heck is that? I don't know, it's a solid, it's a knot-like vortex, but see, all the language has been used already. So this is kind of a fun thing that I'm looking forward to examining. I like to think of it as possibly like battle bots, where you put a whole bunch of topological excitations in a room together, BC together, and then have them battle it out and see who wins. But you could just view it as they're combinations of different topological structures, just as Maxwell imagined that different knotted vortex lines were different molecules. Of course, there are a few other topological excitations that you can get out of this very technique, and we are just now finishing a project on 3-dimensional skyrmions, which has its own unique features, but which, of course, I can't talk about yet. Yeah, with that, I think I'll leave it. I thank you for sticking around as long as you did, and I hope you got something out of this knot thing. And if there were one take-home message, it's that the Hopf vibration is so beautiful. You should, again, run, don't walk. Read something about the Hopf vibration, because it is one of the most remarkable little structures in topology. But I also do want to acknowledge my collaborators again for their immense work on this project. Thank you.